we start with a notebook that's called MACE Practice 1. Everyone went to GitHub and download that? Who downloaded it? Who is struggling or? Yeah.
Is it the same one that's on the Colab?
You can also use the Colab and go through the Colab.
So start again.
Okay.
Hello.
Ik heb een mail gekregen van jou tegen mij. Daarnaast aan instand. Dus ja, als je een ploeg gedeeld is, dan is het straks.
Dat
is wat ik ook aangereikt. Dus ik ga een naam geven in configuration.
Yeah, so let's start with the first tutorial. And the first tutorial is about how to, like an introduction on what it is to fit machine learning potential and like step by step teaching you how do you go about fitting your MACE potential. So the objective is that at the end you understand the data structure that we use in MACE for the for loading the data sets and the referencing what are the MACE parameters that you need to choose when you fit the potential, right? And then fitting and testing. So first thing is like installing dependencies. So these dependencies are not dependencies of MACE itself, it's just for the tutorial. So but you can go and if you run the thing yourself, you can install it. Here I've already pre-run everything in case there are some issues. Okay, so today we're going to try to fit a potential for these molecular liquid carbonates that are electrolyte for batteries. So the first thing when you fit a potential is always understand the data good. So you need to first take a good amount of care about what data you have, what kind of chemistry there are, what kind of system you're trying to model, because this is the first step to then go about fitting the potential. And so these are the collection of molecules that we have in the data set, which are these small molecules that are in liquids. And basically, the first thing that you do to understand the data set, and I don't know if it's big enough, probably not big enough for back. I can zoom more.
So I've done this before in class. No.
So I
We have. I don't have. Do you? I don't need to ask.
So first, that data format. So really the easiest data format for training MACE is the XYZ file. So the XYZ file is like a simple right now we will label that. You will label that with like XTB. So it's a semi-empirical model. And instead of running DFT, usually you run DFT at that point. Once you have collected the data. Here I didn't talk about how you collect the structure. But let's say here I just downloaded a set of structure from a paper and I want to fit the potential. In your case, if you have like a system of interest, then you will collect data and structure of yourself to be able to fit it to your system of interest. So the way we do the labeling here is that, so like here is just a bunch of statistics about the molecules. So you see that most structure in your data set has at least 2 molecules, so it's like dimers. Some have 3 or 4 or 5 molecules, and some are monomers with just 1 molecule. And one thing that is important is when you want to train molecular liquids models, you need to probe both the molecular configurations, but also the interaction between different molecules, which is the non-covalent interactions. So that's why you also include dimers, trimers, extra to also cover the space of intermolecular interactions. These are the breakdowns of the dataset with respect to the composition of the different small molecules, electrolytes. All of that to just remember you that before you put anything, like really understand the statistics of your data set, because this is the single most important thing you can do for making your model succeed. Okay, so now it's the labeling part. So as I said, usually you will use DFT at that point, but here we are going to just use XTB, which is a semi-empirical model, which is much faster, so you can run it on your laptop. If you install XTB, you can label it yourself if you're running that. But usually you would use an expensive DFT. How you choose the DFT for that you need to pick is also problem dependent, depending on the system that you want to approximate. So MACE fits the atomization energy. So you need to have 2 informations inside. You need to have the total energy of each molecules. So you need to do a single point for each of the molecules. But you need also to have the energy of the isolated atom of every element in your training set. So for example, in this training set, there are hydrogens and oxygens and carbon. And so you need to first be able to compute the energy of the hydrogen, the energy of the carbon, the energy of the oxygen, isolated itself. Like just that, because then what MACE will predict is the difference between the total energy and this atomization energy. And the reason why this normalization is important is because usually, if you look at the size of the total energy, it's a big number, it depends on the units, but if you take like something like EV, most of this energy, like 99%, usually comes from the isolated atom energy. And you don't want to fit that because that's like a baseline. So we compute these terms first, and then we sum them, and we subtract the total energy. We subtract them from the total energy. And so that's why here you see that I take my database. So this is, I read the database, and then I append to the database the isolated atoms. So I append the atom of just hydrogen, just carbon, just oxygen, and so basically I have my database plus that. And then I go over, so you see that now you have 3 structures more. And then I go over the database and I call XTB, which is the semi-empirical method that will compute the energies and the forces. And that's how I label the data here. Usually you would call a DFT code yourself. Okay. So let's take an example. So you see, that's the first structure. It has 24 elements. We've computed the isolated atom energies. So in the MACE language, we call these E0s. So the E0s are the energies of the isolated atom. You see the energy of the isolated atom H for XTB is minus 10 eV. The energy of the oxygen isolated is minus 100. Usually, the more electrons you have, the bigger the number gets. And the total energy of that config is minus 1,323 blah, 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 eV. So you see it's big. But actually, when you subtract the isolated atom energy, it's only minus 47. So you see that basically you have 2 order of magnitudes, we have removed 2 order of magnitudes of energies by just subtracting the isolated atom energy, so you make the problem much simpler. And if you divide this number by the number of atoms in the configuration, then you see that for each atom you only need to learn a few EVs of signals, so it's like a smaller range. And so that's a very important normalization. In machine learning, it's always important to normalize your data first to have like a good distribution. And here it's like a sort of physical, physics motivated normalization, because you don't normalize, you could normalize by the average over the data set, But here, one important aspect of why we normalize like that is because once you dissociate atoms, like you take a molecule and then you dissociate it, if you have made your model such that it predicts the exact isolated atom energy, it will go to the correct limits. When you dissociate, it will go to the sum of the energies of the isolated atoms. So it means that you have been forced that the model has the correct limit. And usually that's something we like. Exactly, so now we get only a signal of like a few Ilyes per atom to fix, which is much better. And that corresponds usually to the energy of covalent bonds. So if you look at the energy of formation energies of covalent bonds in organic molecules, it's a few dBs, and basically you're asking the model to only learn roughly this energy range, and not thousands of dBs that correspond to the core electrons. And one reason for that is MACE models for chemistry. So they really describe the atomistic chemistry part of the atomistic structure. We are not interested in the electronic structure, and in particular, that means that what we really want to model is the bonding, the non-covalent interaction, all of these kind of weaker interaction, and everything that is really electronic structure driven, like the core electrons, all of that we don't want. Okay, now we have the data set. We have normalized the data set. How do you go about fitting a MACE model? So a MACE model is a machine learning model. So it has a set of hyperparameters that control the expressibility and the size of the model itself. I was not there, but maybe Gabor went over the MACE model architecture. I didn't put a slide here, but MACE is a message passing neural network. So it has some hyperparameters, and also it's a machine learning model, so it has also you will train it. So you initialize the model with random initialization, and then you need to train it to such to get better. And this training, there is an optimization algorithm to train it, and that also has parameters. Okay, so what are the MACE parameters? The first thing in MACE is the number of channels. So the number of channels controls the width of MACE. And the usual number is 128. So 128 is the default number. And if you want to go to smaller, you can use 64. And if you want to go to a bigger model, you can use 256. But usually I recommend you to only keep the default number, 128. Then there is the maximum order of the message. So MACE is a message passing neural network, so it basically passes information between atoms, and it discretizes this information, the angular part of this information, with spherical harmonics, and that basically gives you the maximum angular resolution of the message passing step. So the higher you go, the more you can resolve small differences in orientations between atoms, but also the more the model gets expensive. So there is always a trade-off about on how expensive you want to be and how fast you want to be. When you do max L equals 0, that's the lowest you can go, and these are for the fastest models. So if you want to make a fast model, you can do L equals 0. The default is L equal 1, and usually I will recommend you to start with the default, so L equal 1 for your application, because it's always better to get started with something that is explicit enough, and then reduce if you need speed. Because if you're not explicit enough, you can have problems fitting the data at all. And so you don't want to get in this loop of not being able to fit the data because you are not explicit enough. So first go with the default, and if you need to get faster, you can reduce that to max L equals 0. The cutoff looks at the interaction range of the interaction that MACE sees in the molecule. So the default is 5 angstrom. So basically, it sees for every given atom, subatom, it sees up to 5 angstrom away. I can show you one. Here. So that's the principle of a message passing network. And what it does is that for every central atom, MACE will look at the neighbors in a sphere and construct interaction within that sphere. here the sphere is quite small, but 5 angstrom means that this sphere goes up to 5 angstrom. And in terms of number of neighbors, like the number of atoms that the central atom sees around to describe its energy, then it's usually around a few 40 or 50 atoms around. So it's not like here that's a much smaller cutoff than what we actually use, because usually we go to much bigger ones. And then what the message passing step is the fact that you first construct representation on this sphere, and then you have a second layer where the central atom sees not only its neighbors, but also the neighbors of its neighbors. So it will, for example, see that this hydrogen has this nitrogen as a neighbor too, and so basically it can construct longer range information that way. And in MACE, we have also a method that controls that, so I'll show you now. Which is this number of interactions. So the number of interaction is the number of times you do message passing. So in MACE, the default is that you do one interaction, two layers, so you do one step of message passing. So here again, it's nice to keep that to a default, so 2 is usually the best. The correlation is looking at the body order of the representation of each layer. So in MACE, when you have a sphere of atoms like that, the central atom sees a bunch of neighbors, and then you construct many-body features. So inside you will construct features that are 2-body, the function of just 2 atoms, but also 3-body, 4-body, 5-body. So all of that, and the higher you go, the more expressive you get. And the and this correlation order is the body order -1. So the default in MACE is correlation order 3, which means that MACE will construct 4-body interaction of each atom at each layer. And that's the correction is the parameter that controls that. Going to higher makes you more expressive but slower, and going to lower makes you less expressive but faster. So that's the correlation here. So again, keep that to the default. I'm just explaining the parameters, but keep that to the default. And that's the angular resolution max equal 3. That also you should keep to the default. Then the other things that you need to set is that you need to set, and there I will go to the example directly. That's the configuration file that you will write to train your MACE model. So the first thing that you do is that you say you want to train a MACE model. So that's a YAML file, it's a text file that you write yourself. There are a bunch of examples in MACE. Then you say, I want to use 32 channels. So here we use a very small model so that it trains very fast. And so also max L equals 0. So these are, and the cutoff is 4 angstrom. So these are the hyperparameters that I told you about. If you don't specify them in the config file, then they will just get set to the default. You don't have to set them. Then the other thing that you need to do is give a name, and also a model set of directories where you will have both the model save, some logging of what's happening, checkpoints if you want, results. Okay. Then you need to give the path to your training set. So remember that we labeled the data with XV, and this is the path to the XV training set. It's an XYZ file that contains the training set, and you need to give it to the train. Once you train a model in machine learning, you have a training set, and then you have a validation set that where you are not training on it, so you're not optimizing the parameters on it, is to check the convergence of your training. So it's like a held-out validation set, where as you go and you train the model, you see how good the model extrapolates to a set of structures. But that you evaluate as you do during the training. So here we say that we take 10%, so 0.10 is 10% of the training set, we use it as the validation set. I see a message with the shape of story. Yeah, the section is recorded. I don't know if you hear me, but the section is recorded that way. It's not. Oh, it should be. It should. Okay. Yeah, so 10% to the validation set, usually 10% is the right order of magnitude. So you want to sacrifice 10% of your data set, your training set, towards the validation set. And then there is a test set. So the difference between the test set and the validation set is that the test set you will only evaluate at the end. Because test set, you don't want to inform your training on the test set. The test set is like some held-out thing that you want, not prohibited by not entering the training itself. Then very important are the keys. So energy key and forces keys. This is the keys that you use to score the XYZ file. So if I go up here, so remember that we did the labeling with XTB. Okay, we did the labeling with XTB, and we did XTB get potential energy that returns the energy, and get forces that return the forces. And we cut that into the dictionary at these keys. So energy XTB, forces XTB. These are the keys where we store the energies and forces. And you need in the file, and you need to tell MACE what are these keys, because you cannot find it for itself. So if you use these keys, you need to leave it here. So here are the keys. The device here is CPU because I ran it on my laptop, but usually it will be CUDA. You put CUDA here to train on GPUs. The batch size, so the model is trained with stochastic gradient descent. It means that basically you go over the training set by small batches of 10 structures, and you update the weights like that. It's not like you see all of the training set at once and then you make an update. You compute the error on the energies and forces for 10 structures, you update the weight, and then you get new structures. So that algorithm is called stochastic gradient descent, and is like the standard algorithm to train neural networks. The number of epochs is the number of time you will go over the full training set. So the model is trained by looking at every structure in your training set, and once it has seen all of the structure and updated its weights, then it starts again from the start and goes over all of the training set again, and it does that 100 times. And basically, what you can see is that if you look at the batch size is the number of structures in individual training steps, and you divide your, let's say you have a data set of 100 configurations and a batch set of 10. It means that for every time you go over the training set, you do 10 updates of your model. So the model will change parameters 10 times. And if you do that for 100 epochs, you will end up having changing the weights 1,000 times in total during your training. Okay, and then you set the seed. I won't go in detail. Once you have this text file, then it's very easy. You can start training your model. Here, we train it through Python, which is not the way you will usually train it, just because it's a notebook. Usually you use a command line, which is that called MACE run train. Once you install MACE, so you git install MACE, then you can just call MACE run train, and it and the path to that config file, and it will start the training. Okay, like here we do that. Like imagine that this is in the command line, MACE run train, and then you do --config, and you put that here, and now you start training. And this is the most important part. So once you start training, you have some logs. So the logs will tell you everything about the training that has happened. First, it will recap to you what MACE version you've been using. So here it says that you are using the MACE version 0.316. That's super important because MACE will change and changes often. So you need to make sure that when you want to compare your experiments to your past experiments, that you use this consistent set of versions. And also, usually I encourage you to update the latest version because we always correct bugs. So if you see here that you are like 5 or 6 generations behind the latest MACE, then it's quite good to update. Then it gives you information about the loading of the data. So in particular, I will not go over the heads now, but you can has different training data that are inconsistent, so that's why here it's just default. It also gives you information about the keys where it's searching for the data. So here it's saying to you that it's searching for the energies in the file at energy xtb. This is super important because if this is incorrect, then the model will not train on the right thing. It will go and look for the data in the wrong place, and therefore it won't do well. So the first mistake is to give the wrong keys here. Like, do make sure if things are looking wrong, usually it's because keys were not provided correctly. And another way to check if the keys are provided correctly is that it says here that it has found 200 energies in the training set, and usually if you have 200 structures, then you know that all the energies were loaded. If you see that this number is smaller than the number of structures in your training set, then that's fishy and you should check that your keys are not incorrect. Because like if you have 200 structures and you have only 150 energies, then there is something wrong. And you will also see on the side that you have also the same for the other courses. So here it says that it has found 200 set of courses. So that's the first thing when you look at your training. Make sure to look at that. Okay. Here it says that you have provided no validation set. Remember that what we did is that we say please use 10% of the training set as validation set. So here it says you haven't provided the validation file. I will use 10% of the training set. Super important, it will save in a text file the indices of what structure it has picked. This is super important because if you want to be reproducible, you need to use the same split of training and validation. So once you have done the training, you can save that file and see that file. If you want to use or check back your training, then you can be sure that you are reproducible. Okay, and then you see here that it has picked 10%, which means that 20 structures will go to the validation state, and 180 will stay in the training set. And then it has found the test set, which is a 1,000 structure that is as loaded. Okay, good. Then here it recaps the E0s, that the isolated atom energies that you have given. This is super important also. Like getting the E0s right, because it is super important. If you get them wrong, then the training will be bad. So do make sure that here, once it's printed, that this corresponds to the value that you really want. Okay. It will print other kind of information. I won't go about that. It will recap the hyperparameter. So as I said, we're using a multiple substitute channel max equals 0 with 2 layers and correction cutoff. And using Adam as the optimizer. Okay, okay, first thing is the training started now. So you see it says started training, reporting errors. Okay, the first line in the error is the initial line, and that corresponds to the error of your model on the validation set with no training done. Okay? It's super important because that means that detects several kind of bugs. So what information that gives you? So you have the RMSC. Everyone knows what RMSC is. Yeah? It's like the square root of the error on the energies. So here it tells you that at initialization, the model makes an error of around 6 EVs, 6,000 EVs. Okay, on the energies, and on the forces, around 2 EVs per angstrom. That's roughly, if you use a model, you train a model from scratch, usually that's the correct number here. If you see that this is too big, like 20 EVs per atom, or so this is per atom, or like 50 EVs per atom, then it means that your E0s are wrong, or you have provided the wrong keys. You need that to be only of the order of a few EVs per atom. This is the first thing to check, the initial validation line. You go there and you check that this is only a few EVs per atom for energies and a few EVs per angstrom for the forces. Really important. Then it will do the training. So initial and then epoch 0, it means that it has went through all of the training set. And as we said, we are doing 100 epochs. So you see that the energies and the forces are going nicely down. So it's 6 EVs first, and then 5, and then it goes slowly down. And so as you keep training, So you train, okay, here, if you do it on your laptop, this will take like 5 to 10 minutes. On the CPU, on the GPU, that will take like 1 minute. The time spent to train the model is a function of the size of the model and also of the size of your training set. So if your training set is very large, obviously it will take a long time. And if your model is very large, it will take also a longer time. It's important that basically you see that things go smoothly down. Usually, it's a sort of the train dynamics is a sort of so the error as a function of the number of epochs. If you plot it like that, it will look like that. So that's the and like for example that's the loss. Okay, so at some point it will plateau, and that's when you will stop. And at the beginning it will go very fast. It's usually not such a good sign if it does something like that. So it goes up. So if it goes up, usually that means that your data has a bunch of noise inside. Yeah, okay. Sorry for the people online. I'm drawing on the board, but just standard variations. So these kind of things you can plot to yourself. And actually, the code base plots it for you. Okay. There is one thing that I want to talk about here is that when you train from scratch, you see at first it will train mostly on the forces. So here you see that the forces they go down very fast. So from 2 EVs it goes to like 200 millieVs here. It's a bit noisy because the validation set is small, so there is a lot of bias. At some point, it will switch, and that's basically because the model will start optimizing the energies more after a while. So first it trains on the forces, and then it trains on the energies, and then that it does automatically. And you see that when it switches to the energies goes down very fast, and at the end, what you see is that you end up having a model that has about 60 millieVs per atom on the energies, and 170 millieV per atom on the forces. So this is a very small model on a very small database, so the errors are quite large. Usually when you train your own model, that's dependent on many things, but you expect that this value is around 1 to 2 millieV per atom, if there is not too much noise, and this value is around 10 to 20 millieV per atom. This is the ballpark. It can be higher or lower depending on what you train on and the size of your model. At the end, it will tell you that it has saved the model. So the code automatically saves the best model that it has found. So basically, it trains models per epoch, and then at each epoch, it evaluates on the validation set, and at some point, if it has the best validation metrics, it will save it. So here it says that it has saved the model at the 68th epoch, so it's not the last model, and it will save models for both the first phase and the second phase. I'll explain to you the first phase you train on forces, the second phase you train more on energies, and it will save the best model of all of each phase. And at that point, you can go down and you see this table. This table, it recaps 3 things. It recaps the training metrics, like MSE on the energies and the forces, and it also recaps the test metrics. And this is the first time you will see your test set. So your test set is bigger than validation set, and you only see it at the end. And you see here, it's quite good news because the test set values are roughly equivalent to the validation set values. So it means that the model has not overfitted. If you see that the test set values are much bigger than the validation set values, it means that your validation is not representative enough. The second thing to check, okay, also it's normal that the training values are bigger than the validation values, so that's normal. In modern neural network, usually you expect the model to actually do quite well on the training set. The most important thing to look at is the relative force error. So here you see that roughly the error on the forces is around 5% of the total force magnitude. And that's the correct thing to look at. Usually if you want something that is stable for doing molecular dynamics robustly, you want that value to not be much bigger than 20%. A good value is around 4 to 5%. A very good value is like 1%. Above 20%, it means that either you don't have enough training data, or your data can be a bit noisy. So you know that DFT has noise itself. So sometimes you cannot. I see that someone raised his hand. I don't know how. I don't know if you can speak. Amir? Yeah, we can. I don't know if you hear me, but you can type your question. I will read it. It's you.
No.
No. Yeah.
So like the version that I downloaded from GitHub seems to have different numbers from this one.
In terms of metrics,
Yeah.
It's not entirely. There are some variants. I mean, if you took the same seeds.
Yeah.
Yeah.
Yeah, but a couple of questions on that. First, the main criteria to select the best model is, I mean, it seems that it's only the RMSE of the energy per atom, right?
No, it's the loss of the validations.
Okay, so what would be the loss in this case?
The loss is, in that case, is the sum of the error of the energy squared plus the error of the forces squared with weights.
Okay.
So there are different loss functions
Okay.
that the model optimizes. And here, usually we use the square loss, which is just something like that.
So it's like a weighted average between
Yeah, exactly.
the RMSD of the energies and the forces.
Yeah.
Okay.
So you have like something like that. And
Yeah.
plus something of the forces.
Yeah.
And obviously here I don't put the
It's fine.
I don't put the. You need to sum over the atoms and normalize them.
Yeah, sure. Okay, thanks.
So that's the loss.
Thank you.
Okay, nice. We have trained the first model. So let's see what we can do with it. So as I said, it has saved the model somewhere, and there is a dot model file, and the dot model file is what you will use to run molecular dynamics. So let's see. Okay.
Sorry.
Yeah.
Another question, sorry.
Yeah.
So you mentioned also that basically you should expect like a decay of the error, right?
Yeah.
But for example, I'm looking at the numbers here, and at some point after you get like the best loss, the errors start increasing a lot.
Yeah.
So is there a way like to program like an early stop or something like that?
Yeah, so that's what it's doing by saving the best. It's basically making sure that it saves that one.
I mean, yeah, but at the end you continue with the average.
Yeah,
so
yeah. Also, if it's very expensive, then it will stop itself after. If it doesn't improve after a few epochs, it will stop itself. Here it's a very easy, a very small training, so it won't stop. But yeah. And also, the fact that it goes up on that example, it's quite not representative of the general case. Usually it doesn't go up.
Okay, it converges.
It converges nicely. Here it's because it's a very small model.
Okay.
And also a very small training set that it does go up. I have a question.
Thank you.
Sorry. Sometimes we can't achieve good accuracy for both energy and forces at the same time, in our experience. I don't know how to access the chat.
I mean, you can just infect.
Yeah, but I couldn't read the end of the question. Yeah, so there are many aspects to getting good energies and forces. Usually if you cannot get good energies and forces, it usually means that there is some kind of incompatibility between them, or you should check your DFTs. It's possible, for example, that your forces or your energies are not converged. One other example is that you have not removed the Langevin term from your forces. So let's say if you train on AIMD data, so that happens quite a lot, when you train on AIMD data, so DFT MT data, you cannot take the forces that you get directly out of the MD driver, because usually these forces contain the Langevin noise of the integrator. So you need to make sure that you take the forces that have no noise. I'm not saying that this is your problem earlier, but that's one thing to flag. Usually, I mean, going to bigger models helps, having bigger training set. So there is like no single answer, but it's like most of the time is also making sure your data is very well converged. So that's really the most important thing. And when I say very well converged, it's in terms of DFT convergence, like consistent steps, K points, energy cutoff, all of these things. The models are very smooth, and so if your data has unsmoothness inside or noise, then the model will just refuse to fit it, which is a nice thing, because in general, we find that models trained on inner DFT data are actually more accurate than DFT itself, because actually the models have less noise. So in general, if things plateau very early, it's not necessarily a sign that the model is getting strong. It's also possible that you don't have enough data or the model is too small. So here I'm teaching you how to train models from scratch. Actually, I wouldn't recommend people to train models from scratch anymore, because another thing to do is to fine-tune models, which should be the next example. But it's nice to learn the basics of MACE that actually I teach how to do.
You also want to answer the question before.
Yeah, what was it? Where exactly we have to mention to initiate train on forces and then switch? Yeah, so the question was how to select the scheduler of forces and energies. And in the config file, that's given by this thing called SWA. Here, when it says true, it means that it will do this two-step training. And automatically it does the cutoff at around 25% of the end. So right now we have 100 epochs. So for 75% of the epochs, it will do the forces, and then 25% it will do the energies. So you only, if you want to disable that, you just put the SWA to force. Okay. We have the model now, it's trained. So the thing you can do is you can evaluate it. So and look at some statistics. So there is a function called evaluate in MACE where you give it the configs, that the file that you want to evaluate, the path of the model, and then the output. And what this function will do is that we take the model, go over all of the configuration in the training set, in the configs that you put, and write a file where it has happened to the file the energies and the forces and the stresses of base of the model itself. So it means that this is a new file with the same configuration here, but with the results of the model. And so here we will evaluate the training set and the test set, and we will do some plots. So let's do some plots. So these are what we call parity plots. So in the first one is energy parity plot. So this is the MACE energy versus the XTD energy. So this is the atomization energy. So you see that the spread is around like 7 eV per atom, because we have removed the zeros. And you can see that the model on the training has quite good prediction. It's around 5 millieV per atom on the energies. On the training and on the test, you see it's barely bigger, so very good agreement. Usually I recommend that people plot the atomization energy and not the total energy. Because here you see, we go to the total energy per atom, and you see that it's much bigger. So actually, you have points that are very far apart. And actually, there are a lot of cases where your metrics might look nice from very far apart, because these are huge energy ranges. But when you zoom in, you see more details. So don't get distracted by the total energy and only plot the atomization energy. And here, these are the forces. And so each point is a force component of DFT, or XTD here, and MACE. And so you want things to be on the diagonal, which means that MACE and XTD can be the same thing. And this is for the training set, and you see that for the test set, it's a bit more noisy. So it means that the model disagrees a bit more on the test set, obviously, because it has only these are new configuration, but it's still decent. The error has not increased too much, and you can looking at this plot is very nice to detect outliers. So if you have a point that is very off, so DFT predicts it as a high forces but makes a low one, or the inverse, then that's a good sign that you should go and investigate that point a bit more. Look if the geometry is weird, look at if the DFT was weird. For example, it was not converged properly. You can go back to see the SCF loop to see if the SCF didn't have a problem. So very good diagnostic to look at these plots. Okay, one thing is that these are like sort of macro statistics. So energies and forces, they don't tell you everything about the accuracy of the model. They hide a lot. And so then you need to go in more details. And to do that, there are several layers. It depends on the system. Usually you will do some molecular dynamics and compute some properties that you will compare to reference values or to experiments set. So this is just the first step. Really. You should not stop at this step. Then we should go further. Here we are studying molecular liquid. And an interesting thing that you can look on the molecular liquid is you can look at not only the force itself, but also you can look at the intermolecular forces. So, for example, if you have every molecule that is labeled J, so this is the whole molecule, you can sum the forces on each atom within a molecule, so though every molecule has a force, which is the force that is acting on this molecule, basically. And you can normalize that, but you can also look at the torque, which is the torque that is acting on this molecule as a whole, because you know that's a liquid, which is composed of molecules. You can look at more detailed properties, and here you can look at things like the vibrational part of the intermolecular forces. All of that is like some more detailed information, and you see different things. So, for example, here that's the total forces. That was quite nice. You see the vibrational forces, which is really the forces of the covalent bonds, like the frequencies of the H stretching or all of these things are very well reproduced. You see the RMSE is very small. But once you go to the intermolecular forces, like translational or rotational forces, which are lower in magnitude, then actually you see that the model does a bit worse. So it means this is normal because the vibrational part of the forces are more short-range and more local, and also easier to learn because they are lower dimensional. Usually they are really a function of the bonding. It's like a OH or something like that. And it's actually something that is super easy to learn. But the non-covalent part of the interaction between molecules, that's much more complex. It has like electrostatic interaction, dispersion interaction, all of that. And therefore, that's why the model is doing a bit worse. But the reality is that once you will do molecular dynamics, if you, for example, want to compute the density of the liquid, which is something that you want to correctly represent, then actually this part matters more than the vibrational part. Because the vibrational part will average out to 0 during the molecular dynamics, but this is what governs the density. So really, looking at more detailed properties and trying to really understand where the model is being accurate and where it's being inaccurate is really what allows you to then go in more detail about how to improve the model. Okay. The second point, the reason why we added dimers and trimers is exactly to learn these things here. Because if you only add the monomers, you will only be able to learn the vibrational aspect, which is fun. Then you can run molecular dynamics with MACE. So the easiest way to run molecular dynamics in MACE is using ASC itself. And there you have a bunch of functions to use that you can use to call MACE as a molecular dynamics. And the only thing that you need to do is create a MACE calculator. So let me go to the, so that's a bit of boilerplate, yeah. So you do from MACE.calculator, import MACE calculator, and then here you put the path to the model. And this will give you an ASC calculator that you can give to ASC to run molecular dynamics. It's as easy as that. The other thing is that you need to define the device. So here I'm saying that I will do the molecular dynamics on the CPU. I highly encourage you to do it on the CPU, which turn the GPU, which will mean that you have CUDA here. And another important point is the precision. So the default D type. So here you see it's a float 32, which means that the model will represent the internal arithmetics in float 32, so single precision. If you want higher precision, you can do 64. This has some influence on some properties, so I want to stress that here because be aware of these things. Questions? Yeah?
How often do you have to switch from float 32 to float 64?
I think usually on the GPU, it's fine to use float 32. Usually, if you want to convert like a very detailed property like the density, I will still make a test run on float 64 and see the impact itself. But I think the part where float 64 helps the most is when you're running NPT, molecular dynamics. When you're running NPT, so not changing the volume and you're only using the energies and the forces, actually float 32 is fine. As soon as you're using the stresses, it turns out that the stresses are much more noisy and sensitive to the precision than float 64. And therefore, I would recommend when you're doing NPT to, for example, converging the density, to at least try 64 and see if it has a big variance. Yeah.
Quick follow-up, does it depend on the system that you're simulating, or is it really just the simulation type, like NPT versus NPT?
I would say mostly the simulation type. I would say NPT is like the most sensitive. We are improving that. And the system does matter for the numerics, but I would say really float 64, I would really encourage it for NPT, or if you do geometry relaxation with like a second order optimizer like type like LDFGS, there it's also nice to use float 64 if you're relaxing the cell too. If you're just relaxing the atoms, basically it's all about whether you're using the stresses or not. Because the stresses are a bit noisy in float 32, so I would say that's the main decision factor. Float 64 is about 2 times slower than float 32. So once you do that, you lose a bit of speed. Yeah.
Thank you.
Do you have a question?
Yeah, no, it was just a bit of a follow-up question because we were also trying to calculate Hessians using MACE models, and we also found that for Hessians you really need to do the float 64.
Yeah, definitely. I mean, the Hessian, basically the error of the noise. The noise is somehow the square root at each time you take the derivative. So once you take the derivative twice, then basically the square root of the square root, and so actually it becomes quite big. Okay, so this is this is some simple launch graph molecular dynamics where you do some molecular dynamics at quite high temperature, so 1200 Kelvin with the calculator, and you write the trajectory here on that pipe. And this is the trajectory, so this is the energy in per atom over the trajectory. So nice thing to look at, the things explode at some point. You can see here. And the temperature, so you want obviously that things thermalize. This is a very short simulation, so it won't reach the thermal equilibrium yet. We are only running 200 femtoseconds for it to be fast, but it has run 200 femtoseconds in less than 1 minute. This is on the CPU. If you run on the GPU and use the proper CUDA kernels, then I don't talk about that, but they are like accelerations of MACE, then usually you can run about 10 million steps per day. So basically, that's about 100 steps per second. So you will have done that in 20 seconds, basically. So much faster than that. Okay. You can visualize the trajectory. The movie, sadly, that doesn't work on my laptop. I don't know why, but you can try on Colab. It might work. Okay, so how do you know if your MD was accurate? Always go back to properties. One of the simplest properties of liquid is the RDF histogram. here of the OH intra. So this is the distribution of the bond length, and you can compare the X. You can do an extensive MD with XTB and compare if the RDF of XTB and the model agrees. So you see that the first peak agrees quite well. The secondary peak, fine, but not perfect. Again, this is a very tiny model, so that's why it's not perfect. But this is actually something that is quite easy to look at. It's the first step. First step of whether you have described the liquid right, you just look at simple RDF, GFR functions, then you will go to compute the density, the diffusivity, and all of that. Okay, so here we are directly computing the molecular liquid itself. So you remember that we've trained only on clusters. So single molecule, 2 molecules, 3 molecules, 4 molecules, and now we try to extrapolate to the bulk. So this is what we call extrapolation from cluster to bulk, which means that you go from finite dimensional clusters to the infinite dimensional bulk. And this is one of the things we really want to do when we simulate liquids, because we hope that we can use very expensive small clusters, converge them very well with a very expensive DFT, and then extrapolate to simulate the bulk liquid directly. So here we've done some molecular dynamics. It's a bit bigger system, so it's more expensive. I didn't put that one. Okay, I didn't put any other thing than the idea that the thing go from cluster to bulk. Anyway, that's the first part of the notebook itself. The first notebook. So basically went over just training from scratch the model, how you can validate your data, looking at easy properties like DFT. I have no clue because we were so late. What is the timeline for the thing? Is it like 10 minutes or 1 hour?
For coffee, yeah, I think if we do a break at 5, it's good, yeah. So in 10 minutes, if that works for you.
Yeah. I guess I can introduce the next notebook before the break. But we can do the break now. Okay, let me introduce the notebook and then we do the break. So the second notebook is about iterative training. So iterative training is a bit the old school way to develop force fields, which is that usually you train your model on, let me show you a video. Usually this is what used to happen back in the days with machine potential, is that you take your database like we did, you fit your potential, and then you run MD, and things explode. So that was the usual thing with the old potentials. It explodes, then what you have to do is that you take the frames that exploded, you recomputed some new DFT with it, you put it in the potential, and you hope that this loop converges before the end of your PhD. If you can graduate in time. And sometimes, most of the time it does converge, but usually it's several years for it to converge because that's a very painful process. Okay, that loop, which was the nightmare of many of your previous colleagues, and maybe some of you, if you are here for a long time, then that's called iterative fitting. Usually, right now, people no longer do it the same way because you use foundation models, and that will be the last notebook. But just for embracing our history, we should go over this thing together. So that's the second tutorial, where we'll basically go over how do you do iterative fitting, but also what does it teach you about how you do potential. And the way we will do that is that we will will train a very small model. So remember that the previous model, which never exploded, even though it was trained on 200 structure, it was a very small model, it didn't explode. It turned out that newer models like MACE tend to not explode as much, even with small amounts of data. But here, to make sure that it explodes, actually, it won't explode, but at least it will do something weird. We reduce the data set even more, and we fit it on only 50 configurations. So even less, 50 is usually not a good number for your training set. Usually, when you do your own training set, it's 7,000 if you train from scratch. So here we are order of magnitude less. And we will keep a very small model, and you see that the training will be just, actually no, it's 20 configurations and 50 for the validations, right? And we will train the model. I don't know if we, I think we should take the coffee break now, because then I'll go over the rest of the look after. Right? Yeah, thank you. I hope that there is another, because it's so late.